Okay, we're live. So happy spring break. I've got a couple free response questions we'll be doing today, but first I'm going to quickly review everything about curve sketching as fast as we possibly can. So these are just vocab terms that we'll see in a minute. So all the algebra stuff out of the way. Our x-intercepts whenever we cross the x-axis, y-intercepts are when we cross the y-axis. Vertical asymptotes are straight lines that our function cannot cross. This is whenever the denominator is equal to 0 and the numerator is not also 0 at the same point, which means it's a problem with the bottom of our fraction that we can't get rid of. Removable discontinuities are holes. These are when the denominator is equal to 0 but the numerator is also equal to 0 at the same point, which means we can get rid of the problem. Removable discontinuities, when you're graphing them, look like a line with a hole in it. A vertical asymptote is an infinite discontinuity. Our horizontal asymptotes are horizontal lines that our function approach towards the end of the graph. It is possible to have two different horizontal asymptotes. So that could be something like an absolute value function, where we approach maybe -3 on the left and +4 on the right. Slant asymptotes are similar to horizontal asymptotes, so they're a line that our function will approach towards positive or negative infinity, but instead of a horizontal line, it's slanted. Our derivatives tell us the slope of a function. So if we want to know the intervals where our function is increasing or decreasing, we would derive. If we want to know the critical points, we would derive. Critical points are any points where the slope is equal to 0. Our second derivative tells us concavity. That's the shape of the curves. So I have this chart here. On the left side, for both of these, our function is decreasing. But for the top one, I am concave up, so sort of like a U shape. For the bottom one, I'm concave down, like an upside down U. I am increasing for the rightmost ones, both on the top and the bottom, but on the top one we are increasing in a way that is concave up, which means we're curving up as we're increasing, versus concave down, which is what the bottom right looks like. Okay, so I've got one long form example that I sent you guys. I'm not going to go over all of it. I will point out, though, for the part that everyone in my class seems to be missing, are slant asymptotes. For slant asymptotes, we have to use long division first. So divide out, and then whenever you get your remainder, just forget about the remainder, and that will end up being your slant asymptote. Okay, Nathan says he just got disconnected. So I'm going to see if I can bring him back in. Okay. Vivian is still there?
I'm here listening.
Are you listening? Okay.
Oh, hi, Mr. Brandon. Now, my PC just got disconnected.
Okay, cool. Can you see the screen still?
Yes.
Awesome. Okay, so I've got one example up here that's already half worked out. So if I zoom in here, what have I marked in blue?
The maximum and minimum.
Okay, so these are the relative extrema, the maximum, the minimum. These are also critical points where the slope is equal to 0. My leftmost one is the relative minimum. Is this relative minimum the absolute minimum?
No.
No, why not?
Because it keeps getting smaller when it's going to the right.
Right. So absolute minimum is the smallest possible value on the entire function, but a relative minimum is just relative to the points around it. What did I mark in purple? That's this mark here.
Is it the inflection point?
Perfect. So that's the inflection point, or the point of inflection. So that's the point where the concavity changes from concave up to concave down. It is possible for our point of inflection to happen when our function is undefined. Point of inflection is any time when a concavity actually changes. It's also possible to have a function where the concavity does not change when our function was undefined. So that would look something like this. So if that's my coordinate plane, I could have something like a vertical asymptote here at my black line, and our function doing something like this, where we are concave up before that, and increasing, but also concave up after that, just decreasing. This does not count as a point of inflection because we didn't actually change concavity. If I did change concavity, so if that last line had looked like this instead, where instead of being concave up, we were concave down after that point, that can count as a point of inflection. Alright, so let's take a look at a couple examples. So this is 2011 question 4. We have our continuous function f drawn here. If the video is not clear, you can download the one from WeChat, and that should work as a PDF. So we're defined from -4 to +3, and we're told that we have 2 quarter circles and a couple triangles, so one line here. And we're also told that g of x is equal to 2x plus the integral from 0 to x of f of t dt. The first thing they want us to do is find out the value of g at -3, and then find g prime at x and g prime at -3. So if I wanted to figure out what g at -3 would be, what would I have to do?
Integrate from 0 to -3.
Perfect. Okay, so we are getting g at -3. So for this first part, the 2x, I can just plug that straight in. 2 times -3. The second part, you're right, I'm going to integrate from, plus, the integral from 0 to -3 of f of t dt. Okay, if I'm integrating from 0 to 3, so I'm looking at all of this area here. How can I find that area?
Which area are you talking about?
Oh, I'm sorry. Actually, I'm looking for 0 to -3, so I'm looking for this area here. How can I find this area of the quarter circle between 0 and -3?
Integrate the function again.
Okay, I want to integrate the function, but we don't have a function given. We were told that these are quarter circles. So how could I find the area of a quarter circle?
Just 3 times 3 times pi divided by 4.
Perfect. Okay, so that's pi r squared divided by 4. Our radius is 3. So that's 9 pi over 4, but we integrated backwards. We went from an upper bound to a lower bound. So instead of adding, I'm going to subtract. I'm subtracting 9 pi over 4. Okay, so g at -3 is -6 minus 9 pi fourths. The next thing we need to do is figure out what the derivative would be. So I've got g prime at x. We'll get a general form first. What happens when I derive the first part?
2.
2. And what happens when I derive this integral?
Equals f of t.
Okay, I'm going to derive in terms of x. So I'm actually going to integrate to get, I'll call it capital F. And then we'll derive to get back to f of t. But when you integrated, you would have plugged in x, so our variables are going to change. So this is going to be f of x times dx, which is 1, since we're deriving in terms of x. minus f at 0 times d0 with the derivative of any constant is 0. So our general form is 2 plus f of x. And then I can plug in negative 3. I did have to write that as a separate function because they did tell us to find g prime at x. So this is our evaluating g at negative 3. I've got 2 plus f of negative 3. What is f of negative 3?
Zero.
0, perfect. So I've got 2 plus 0 or 2. Any questions on part A?
No.
Okay, part B. We're looking for the x-coordinate of the point on which g would have an absolute maximum on the interval, and then justify your answer. So how can we tell when a function has an absolute maximum?
Where its slope turns into 0.
Okay, so that's a relative maximum. A relative maximum, the slope would be equal to 0, and our slope would be changing from what to what?
From increasing to decreasing. Oh, so compare like all the different critical points.
Okay, so I need to look for a critical point that is a relative maximum. So that's a point where our slope changed from increasing to decreasing, but I also need to be worried about possibly changing back to increasing and then ending up with an endpoint that is higher than my relative maximum. Or, if I went the other way, having a start point that was higher than my relative maximum. So, for an absolute maximum, I will need to test the start point and the end point as well. Okay, so for this one, let's look at our critical points first, and then we'll see if it makes sense to test the endpoints. So, do I have any relative maximums looking at this graph? Since I know g prime at x is 2 plus f of x, are there any points where f of x would make g prime equal to 0?
Negative 3.
Okay, x equals negative 3, f of x is 0, so g prime would be 2, not 0. We said last time our g prime at x was equal to 2
it would be
plus
0
f of x.
for x.
So we need f of x to be equal to how much in order to make g prime at x equal to 0?
Equals to 2x.
Okay, not 2x.
Equals to negative 2x.
Just negative 2, actually. So we need f of x to be equal to...
derivative.
This graph is just f, not the derivative. But g prime at x is what we're going to be looking for the derivative of g. The derivative of g will get us back to regular f of x for the y value. So I'm really looking for this point here, where f of x is equal to negative 2. Now I could try to look at it from the graph, but we do know that this is a line. So we could use the equation of this line in order to figure out exactly what our y value would be, or where our y value would be equal to negative 2. So what's the equation of this line?
Square root 9 minus x squared.
I think you gave me the equation of the curve here for the circle. I'm looking for the equation of the line of f from 0 to negative 3, because I want to know when this function is going to be equal to the y value negative 2. We know the end of that leftmost circle is going to be negative 1 at its lowest point, so that's not low enough to make our g prime x equal to 0. So we're actually looking for this point here. I'm going to call point A. Okay, to find it, I need to know what the equation of this line is that I'm highlighting in yellow. So how can I find that equation?
So the slope would be 6 over 3, so negative 2.
Okay, this
Negative 2x plus 3.
okay. F of x is negative 2x plus 3. Perfect. So if f of x is negative 2x plus 3, and I want to set this equal to negative 2. What happens when I solve for x?
X equals 2. X equals, 2.5.
Okay, 2.5. I'm going to write that as 5 over 2, but you're right. And I'm just going to check on my graph to make sure that makes sense. So here's 1, 2.5. Should be about here-ish, and that is about where we're equal to 2. Okay. The next thing I need to do is prove that this is actually a relative maximum. We just proved that it was a critical point. So go ahead and write down here. Our g prime at x is equal to 0 when x is equal to 5 over 2. And then we need to prove that this was relative maximum. So looking at our equation for g prime at x is 2 plus f of x. Before this point, would g prime at x be positive or negative?
Positive.
Positive. Okay, what about after this point?
Negative.
Negative, okay. So I could say something like this. G prime at x is greater than 0 on the interval from negative 4. Oops. Included, actually. To 5 over 2, not included. And g prime at x is less than 0 on the interval 5 over 2, not included because it was 0, all the way till the end of our graph at 3. Okay, so we have a relative maximum for sure. After our relative maximum, our function decreased until the end of the graph. So that means our original function did something like this. We were increasing until we hit our relative maximum, and then we decreased at the end. So because I was increasing and then decreasing, do we have enough evidence to prove that this was the absolute maximum?
No, like only for 0 to 3, since the previous ones there might. Oh wait, there's no other critical points. So yes, this would be the relative maximum.
Okay, this is the relative maximum. Is it the absolute maximum?
Yes.
Yes, it is the absolute maximum because we know that we were increasing from our start point to the relative maximum, and we were decreasing from the relative maximum to the end point. So because there's no other critical points, since there are no other critical points, G has an absolute maximum at x equals 5 over 2. Okay, normally we would test the start point and end point, but we have enough information that we already know the start point and end point are lower in y value than that relative maximum. Okay, that was the tricky part. The next one, I want to find all the values of x for which the graph of g has a point of inflection. What has to be true about g of x at the point of inflection?
It will have 0 for the second derivative.
Perfect. Okay, we already have the general form for the first derivative that we got in part A, so I'm going to take that general form and we'll derive it one more time. So our general form was g prime at x is equal to 2 plus f of x. What happens if I derive that one more time?
F prime x.
Perfect. Okay, so our second derivative is equal to the first derivative of f. So I need to see, are there any points where the first derivative of f changes sign? So are there any points where the slope of this graph that's showing changes sign?
At -3 and at 0.
Okay, only at 0. This graph is the graph of f, not the graph of f prime, so that means we're just looking at the slope. Okay, so we do change our slope from positive to negative of f at x equals 0. F prime of x changes sign only at x equals 0. Therefore, g has a point of inflection at x equals 0. Awesome. Okay, last one. The average rate of change of f on the interval from -4 to 3. Oh, find the average change of f. And then there is no point on this interval where f prime is equal to the average rate of change, so explain why this does not contradict the mean value theorem. So first, how can I get the average rate of change of f on this interval?
Find the slope from the first point to the end point.
Okay, cool. So that's my average slope from -4 to 3. So that's f at 3 minus f at -4 over 3 minus -4 is my average slope of f. Okay, I'm gonna have to go back up here. Okay, so we were given those points. So f at 3 is -3, and f at -4 is -1. So what will this give me?
One. Oh wait, no. 2/7. -2/7.
-2/7, that's good. Okay, and then last part, we need to explain why, even though there is no point between x equals -4 and x equals 3, where the slope is, where the derivative is equal to that slope, why does this not contradict the mean value theorem?
So there's a turning point for the slope, so that means that there's no sudden jump. So there's a turning point because the slope is different from beginning to the end.
Okay. So for the mean value theorem to be true, you're right. I'm just going to reword this a little bit. Our function would have to be continuous and differentiable. Which part of that did we fail? Which of those conditions?
Differentiable.
Okay, at what point are we not differentiable?
0.
Okay, there's actually 2 points, so what's the other point we're not differentiable?
-3.
Perfect. Okay, so I can write something like the mean value theorem only applies if a function is continuous and differentiable. But f of x isn't differentiable at x equals -3 and x equals 0. Okay, zoom out a bit. Any questions on the first one?
Can you please explain like why would -3 would be not differentiable, since the slope would both be infinitely large for this point?
Sure.
Oh, I think I got it.
Wait a minute. Actually, I'm not sure that's true. As I approach -3 from the right, my slope is still going up. Okay, these two circles are not the same size. I would expect that the rate of increase for the larger circle is going to be different than the rate of increase for the smaller circle. So, no matter how close I get to the point where we are infinite, the same distance apart is not going to bring me to the same y value. Or the same distance apart is not going to bring me the same rate of change. If I had one function that was going up to infinity at a rate of, we'll say, (40 plus e to the 1 over infinity), and I had another function that was going up to infinity at a rate of x to the x power, I would expect this function to be increasing faster than this function, even though they're both going to infinity. On my left side, my rate of increase is going to be different than my rate of increase for this other circle, even though they're both approaching infinity from the left and from the right. Does that make sense?
Yes.
Okay. Alright. Good question. Trickier than I thought it was at first. Okay, next one. So this is same year, but the different form, I think. So I've got a differentiable function that has a domain of all positive real numbers. We know that its derivative is this function here. For all x values that are greater than 0, so we don't need to test any x values and all that. First part, I want to find the x-coordinate of the critical point of f and determine whether that point is a relative minimum, a relative maximum, or neither, and then justify our answer. So first part, if I wanted to get a critical point for this, what would I do?
Find the zeros of f prime.
Okay. What's the only zero that we have for f prime?
4.
4, okay. So f prime x equals 0 when x is equal to 4. And then I do need to test to see is that a relative minimum, maximum, or neither. So what would you test?
The left side and the right side.
Okay, so let's plug in a number. What number do you want to plug in?
0 and 5.
I can't plug in 0 because that's not in our interval.
Oh yeah. 1 and 5.
Okay, so let's plug in 1. When I plug in 1, am I going to get positive or negative?
Positive.
Positive. So I could say f prime of x is greater than 0 on the interval when 0 is less than x is less than 4. If I had plugged in 0, I would have been divided by 0 as well. But then for the other side, what happens when you plug in 5?
It's negative.
Negative, perfect. So we are less than 0 on the interval where x is greater than 4. Okay, so what can we conclude?
So it would be a maximum, a relative maximum. Actually, the absolute maximum for f prime.
Okay. You're right, but we were only asked to determine whether it was a relative maximum, minimum, or neither. So I'm going to stick to relative maximum for the wording, because that's what they asked for here. But you're right. F of x is a relative maximum at x equals 4. Okay. Then for part B, we need to find all intervals for which the graph of f is concave down and justify our answer. So how can we figure out when the graph is concave down?
Find the derivative of f prime and find the zeros.
Okay, we're going to find the derivative. So I'm going to copy f prime x really quick since I'm cutting it off here. F prime at x is equal to, actually I'm going to distribute this in to make it easier for us to derive. So this will be 4x to the negative third power minus x to the negative fourth power. So what will happen to my second derivative of f?
Negative 12 times x to the negative fourth power.
Okay, keep going.
And positive 2x to the negative third power.
Oops. You're right. Okay. I need to find out all intervals where this is concave down. I'm going to do something a little bit different here then. So I'm actually going to factor a couple things out of here so that I can see when this is going to be equal to 0 a little bit easier. So what could I pull out that is in common?
X to the negative 2, the second power.
It's the negative 2. I could pull out more than that.
And also 2.
Okay, I'm going to pull out the 2. I'm actually going to pull out x to the negative fourth power. If I pull out x to the negative fourth power, what's left for my first term?
Just -4.
Uh,
12. -12.
okay, so I'm pulling out 2x to the negative fourth power, so that's going to give me a negative 6. If I pull out 2x to the negative fourth power from 2x to the negative third power, what will I be left with?
X.
Perfect. So I have, if I rewrite this, 2 times x minus 6 over x to the fourth power. Okay, so what value would make this equal to 0?
-6. 6.
Okay, positive 6. And then we need to figure out when this is concave down, so what values will make this negative?
X that is less than 6.
Perfect. So on the interval, starting at my start point at 0, from 0 is less than x is less than 6. We will be concave down, so therefore f is concave down on the interval 0 is less than x is less than 6. Okay, that's good. Last one. Given that f of 1 is 2, we need to figure out what the function of f would be. So I've got f prime right now. What would I have to do in order to get to f of x?
Integrate the function.
Perfect. So I do need to integrate. What am I integrating to? So from what to what?
From f prime to f of x.
I mean for our x values, so I'll integrate from x equals what to x equals what?
From x equals 0.
Okay, I actually can't do that.
Oh, to the x value.
Okay, I'm going to integrate to the x value, but my start point's not going to be at 0 because we don't know what the start point was at 0. So what should my start point be?
One.
1, perfect. So I could say something like f of x is going to be equal to our start point, f at 1, plus the integral from 1 to x. It'll give you the change in y value from 1 to x. And that could be a negative change in y value if I go from 1 to 0. So I'm integrating, I'll use our simplified form that we have up here. This is 4 x to the negative third power minus x to the negative 2 power in terms of x. Probably should have called that a different variable actually, because I've got an x imp here already. I think I'm going to do that. So I'm going to change these x's to some other variable. T, dt. Okay. So what's going to happen when I integrate?
The first term become t to the negative fourth power.
I'm gonna add
negative.
Okay, t to the negative 2 power.
T to the negative 2t to the negative second power.
Positive or negative?
Negative.
Okay, negative 2t to the negative 2 power. I'm going to go ahead and throw parentheses here because I'm going to add that to afterwards. I'm going to plug in our bounds. Okay, what about this negative t to the negative 2 power?
um, t to the negative 1 power.
Perfect. So plus t to the negative 1 power. And we were integrating from 1 to x. So I'm going to plug in our upper bound and lower bound. So what happens when I plug in our upper bound?
It's 2 plus negative 2 plus 1, which is 1.
Okay, I'm going to plug in my upper bound first. So I'm going to plug in x.
Oh, it would be 2 plus negative 2 divided by x squared and 1 over x.
Okay, and then we'll subtract our lower bound.
Minus 1.
Okay. So I've got f of x is equal to, I've got 2 minus minus 1, or 3, minus 2x to the negative 2 power, plus x to the negative 1 power. Do we need to do anything with that? No, just determine. Okay, we're set. Any questions on this one?
Oh, and also add a constant.
We actually don't have to, because we integrated with bounds. So if I'd had a constant, that plus c for my upper bound would have subtracted the plus c for my lower bound, and they are the same constant because they came from the same integral. So we actually don't have a constant.
Oh, I hear it.
Okay. Let's try to rush one more. So we've got...
so the like the 1 to 2 isn't really a necessary information, right?
That is necessary information. That gave us the start point. So without that start point, we could not have integrated definitely. We would have had a plus c in our answer. But because we had that start point, our original function will be our start point plus the change. So that's my y value plus the change in y. My original y value is f of 1, so that's where we got this 2 from. And then my change in y is my integral, as x changes from 1 to x of our f prime. Because when I integrate that, I'll get f of x. So that's how much did f of x change from f of x to f of 1. If I add the change from 1 to x to where we were at 1, then I should get where we are at f of x. Does that make sense?
Yes.
Okay. Any other questions on this one?
No.
Okay, sorry I rushed you. Let's jump to 6. So I've got another piecewise function defined here. Be careful, this graph is the graph of f prime, not the graph of f this time. Okay. So we have f prime is equal to g of x from negative 4 to 0, and also 5e to the negative x over 3 minus 3 from 0 to 4. Our graph of f prime is shown here. It has intersects at x equals negative 2, and x equals 3 ln 5/3. I'm going to go ahead and write that on the graph before I forget. So our intersect there is 3 ln 5/3. The graph of g on the interval from -4 to 0 is a semicircle, and f at 0 is 5. Okay. First one, I'm told that from -4 to 4, find all values of f for which we would have a point of inflection, and then justify your answer. So if I'm looking for points of inflection, what part of this graph am I going to be looking for? Or what should I be looking for?
For the maxima and minima.
Okay. My point of inflection is going to be when the second derivative changes. That's when the first derivative of this graph changes sign. So what two x values will the derivative of the graph that's showing change sign?
-2 and 0.
Okay, perfect. -2 and 0. I'm going to write this. I'm going to say something like f prime x changes from decreasing to increasing at x equals -2, and from increasing to decreasing at x equals 0. Therefore, f has a point of inflection at x equals -2 and x equals 0. Okay, perfect. Part B, we need to find f of -4 and f of 4. So I'm going to do the same thing we did last time. We're going to go from a start point and then add our change in y value. So if I wanted to find f at, I'm going to do -4 first. What's my start point?
Two.
Not 2. So we need a point that we know the y value for on the original graph.
Zero, which is height.
Okay, cool. So I'm going to start with f at 0, and then I'm going to add our change in our y value from what to what?
From -4 to 0 and 0 to 4.
Okay. I'm actually going to go from 0 to -4, so I have to start from my start point. So this is actually going to work backwards for that first integral. I'm going to go from 0 to -4 of my derivative. From 0 to 4, my derivative is going to be g of x. Which means I'm going to have to integrate this this circle. They told us somewhere here. Semicircle. Okay. So starting with this first one, if I zoom in here, I want to integrate the area underneath this curve. So I'm going to take this whole box that I am boxing it in blue, and we're going to take away the semicircle to get this new area in yellow. Okay, what's the area of the semicircle?
2 times pi.
What's the area of the whole box?
8.
Okay, so that means this whole yellow area is 8 minus 2 pi. Here. Okay, so I have 5. If I'm adding from 0 to 4, that's the same thing as subtracting from negative 4 to 0, so I'm going to subtract 8 minus 2 pi. Should give me f of negative 4. So that'll be 5 minus 8 is negative 3, minus negative 2 pi is plus 2 pi. Okay, and then I also need to get f of 4. So how could I set up f of 4?
Integrate ln.
Okay, I'm going to do that, but I need a start point first.
Oh, from 5.
Okay, from 5, that's f of 0. Plus the integral from what to what?
From 0 to 4.
Okay, cool. From 0 to 4 of our function, which was 5e to the negative x over 3 minus 3. In terms of x. Okay, so if I integrate that, what's going to happen when I integrate 5e to the negative x over 3?
E to the negative x over 3 times times negative 15.
Okay, perfect. And then what happens if I integrate negative 3?
Negative 3x.
Okay, and we're going from x equals 0 to 4. Okay, so then I'll plug in our bounds. This will be 5 plus negative 15e to the negative 4/3 minus 12 minus negative 15e to the 0 is negative 15 minus 0. Okay, so that gives me negative 12 plus 15 is 3, plus 5 is 8, or 8 minus 15e to the negative 4/3 is equal to f of 4. Okay, that's all I asked us to do. Find f of negative 4 and f of 4. Last one. Find the value of x for which f has an absolute maximum, and then justify your answer.
So it would be either the starting or ending point for negative 2 and ln 3 ln 5 over 3.
Okay, if I'm looking for absolute maximum, let's get the relative maximum first. So, which point is the relative maximum? Negative 2 or 3 ln 5/3?
The second one.
Second one, 3 ln 5/3. That means we were increasing because f prime is positive from our start point to 3 ln 5/3, and then we were decreasing after that. So is x equals 3 ln over is x equals 3 ln 5 over 3 the absolute maximum or not?
Yes.
Yes. Okay, so I'm gonna write this out. F prime at x was greater than 0. On the intervals, -4 is less than x is less than -2, and -2 is less than x is less than 3 ln 5/3. So I could say, so f is increasing on these intervals, but f prime x equals 0 at x equals 3 ln 5/3, and f prime at x is less than 0 on 3 ln 5/3 is less than x is less than, what was the last round of our 1, 2, 3, 4, 4. Therefore, x equals 3 ln 5/3 is the absolute maximum of f. Okay, any questions on anything?
No.
Cool. Thanks for staying with me. We are 5 minutes over, but we had some trouble at the start. I will go ahead and post this to YouTube for everybody else, but thanks for coming.
Oh, got it.